Hi everyone. Hope you are able to see my slides and hear me properly. Let's wait for 2 more minutes, then we can start. Okay, let's get started. Good evening, everyone. Welcome to the week 7 live session of Digital Design with Verilog. First, let me introduce myself. The students who are joining for the first time. My name is Bushi Ansa. I'm a research scholar at the Family School of Data Science and AI, IIT Palakkad. And I will quickly go through the logistics of this live session. We are doing the live session every week Sunday. It's a 2-hour live session from 6 p.m. to 8 p.m. In this live session, we will have a quick recap of the previous week post content, and we will also have a problem solving section. And the section is mainly focused on your assignments. The problems will be similar to your assignments, not exactly the same questions. And time will be allotted you to solve each problem, and you can post your responses in the chat box. And if you have any doubt from the previous week and or any question you want me to solve, then you can also post your queries in the chat box, or you can ask me at the end of the session. And after the session, we will provide the recording of the live session, and we will also share the slides you can access through HP, which is made by NPTEL, which is available in the Facebook. I'm not audible. Is my voice clear now? Is it clear now? Am I audible? Is my voice clear to you? No. What about now? Is my voice clear? Am I audible to you now? Am I audible? Am I audible now? Is my voice clear to you now? Am I audible now? Thank you. We can continue. So this is the syllabus of this course. The first half is all about switching algebra, the number system, the combinational logic block. And this week we are also continuing the combinational logic design and programming using HTML. And the second half of the course is mainly about the sequential circuit design, includes flip flops, state machines, registers, counter, synchronous and asynchronous sequential circuit. When I dive into this, we will also learn about the basics of FPGA application. So this week we are going to learn about arrows, subtractor and multiplier. So we'll start with the simple bit adder, half adder. You have two simple bit input, x and y, and you will have sum and carry. When both inputs are 0, 0, then sum will be 0, carry will be 0. And x equal to 0, y equal to 1, sum is 1, carry is 0. Then x equal to 1 and y equal to 0, sum is 1, carry is 0. When x equal to 1, y equal to 1, then it will be 2, right? So sum will be 0 and carry will be 1. So how we can write the expression for sum? X bar y plus x y bar. This is the x coordinate. We can write it x x and y. And carry x. So this is a two single bit adder. So you will have two inputs with the single bit. Now our aim is to create an in-bit array. For example, if we take a 4-bit number 1011 0011, what will be the value? If you add here 1 plus 1 0, you will have a carry 1. 1 plus 1 0, and here you will have a input carry, so it will be 1. And here also you will have a carry 1 1. So here you are adding 3 bits. The inputs and the input carry. So this carry is reduced by the previous one. So for this addition, you are taking the carry from the previous one. So next we are moving to the similar adder. So there you can take 3 units A, B, C in. That is the carry in. You will have carry out and you will have sum. So 3 inputs, 3 single inputs and 2 outputs, carry out and sum. You have 8 combinations. 0, 1, 1, 7, 0, 1, 1, 7. So can this what be the expression of sum? Data movement, stealing, product, being, stealing, so this is the expression of sum. Carry, you can draw a PMF to find out the nearest expression. So this is the expression of sum and this is the expression of carry on. So when you draw the logic diagram for this grouping, you will have a 211 logic design. Here you will have AND gate and OR gate. For this also you will have AND gate and OR gate. It's a 211 circuit. Now what we are going to do, we are going to optimize the area of this design. So here you will have 12 AND gates and 1 OR gate for sum. And for carry, we have 3 AND gates and 1 OR gate. So in order to reduce the you need to reduce the logic gates. So in order to get the efficient version of the PID, we can do a multi-linear optimization using common sub-expression. So this is the expression we found. We are going to optimize this. So this is the expression of an excited. Here, this can be considered as A and this five can be considered as B value. A argument B. So we can write it like AXM, AXM, speaking. So this is the optimized expression for sum and carry out is this one. So previously we were doing independently for sum and carry out. Now what we are going to do, we are also trying to find out the common sub expression for this sphere and sum because the inputs for the carry out and the sum are the same. So if we can find out in common sub expression that is the multi-level optimization, then we can minimize the circuit again. So here so this we can write it like this. This is mainly to find out the common sub expression between the sum and the sphere. So time this. If we take C value, it will be A bar B plus A B bar. So A B plus C A X. So this is the an example of multi-level optimization for multiple output design. Now we are going to draw the logic diagram. Okay, this is the logic diagram of the extreme and the field extension. PM expression is AB plus BPM plus AP. Okay. So we want to optimize this result. We are trying to take an addition ratio of the full ladder. So for that, we have to find a common expression between the sum and the speed. For this, what we are going to do, we are going to take this pair and this one as individual ingredient. So from this, we will get this expression. By simplifying this expression, we will get this thing. AB means P in A is of B. So when we draw this logic diagram, from this logic diagram, we can understand that we can construct this polarity using two half angles. This is one half angle, right? And this is another half angle. So you can construct this ladder using two half orders and then is this thing visible now? So you can construct this ladder using two half orders and one pancake. So previously the expression was for some this one. So you have color always and one orbit. And for pancakes, it's a 3 into pancake. And for carry, it is 3 2 into pancake and one orbit. So we were doing for some and Sion circuit independently. But we can, like, we wanted to optimize the area of the business. That's why we are doing all this optimization. So using two half orders and with an orbit, we can construct the full ladder. So this is the area optimized merging design. So here you have total 5 gates are used to implement the full ladder. Is that clear? Is it visible now? Are you able to see the model? Okay. So this is the official implementation of full ladder, area optimized full ladder. So if you want to create a multiple bit adder, you can connect full ladders like it's showing. For example, 5 bit carry adder. That is, your carry in will be propagated towards the last logic gate of the design. So if you have a 2 bit numbers, you will have a input carry, and this provided is going to copy LFP of the 2 binary numbers along with the carry, and you will get the sum. And here you will have A1, C1, and the next bit A1, D1. It is going to give you S1, and this one is P2, and this ladder is going to perform the adjustment between C2, A2, B2, and it will give you some S2 and carry C3. This ladder 3 is going to perform addition between A3, B3, and C2. This is going to give S3 and C8. So this is a repeat carry address. That is your repeat carry is subdivided towards a MSB of it binary element. So if it was an unoptimized design, what was the population delay for one ladder? This was unoptimized design. So in this is a two-level raising different for sum and carry. So if you have a unit ladder for an optimized design, the delay is n. For optimized design, so which is a critical part. Here you have, like, for getting sum, this is the part, so getting the carry, this is the part. So you have three gates. So if you assume one delay for one gate is 1 nanosecond, then it will be 3 nanoseconds. So for n bit adder, the delay is 3n. So if it is a 16-bit adder, then the delay will be 3 into 16, that is 38 nanoseconds. So this is the critical part delay. So you need to consider if the clock period is greater than this. For example, 50 nanosecond for clock period. If it is a 64-bit, then it will be 3 into 65. It will become 192 nanoseconds. So if you look at repeat carry adder, the delay is high. That is the one number bottleneck of this design. It is not fast. So we need to design an adder which could overcome the ripple effect of the carry. This is because of the carry propagating from the immediate block to the next block. So if you can compute the carry for each stage independently without waiting for the carry from the previous block, then we can reduce the delay, right? So that's why we are going to design the next order carry increment. But then I will explain why it is going in. For a single ladder, this is the design for the ladder setting. So here we need to find out the critical path. So for getting the sum, the path is going. One path is this. Okay. And for finding out this carry, this next path is this. Is it clear? Or should I draw it again? So here you have three gates. So if you assume 1 nanosecond has delay, population delay, then it will be 3 nanoseconds. Here it is 2 nanoseconds. So you need to consider a clock period of delay. So here from the output, from the input to the output, this is one part, and this is another part. So you will have to choose the longest path for the critical path. So suppose assume if it is 1 nanosecond for all the gates. So longest delay you have to choose. It is 3 nanoseconds. So your clock period should be greater than your critical path delay. So this is the optimized design of the ladder. If it was unoptimized, it was a two-level logic design, so it was 2n. For optimized, it was 3n. For NP, this diagram is only for one ladder. For NP, it will be 3 NP. N-bit binary adder. Is that clear? So if it is a 16 bit, then it is 3 into 16, 28 nanosecond. If it is 64, then 192 nanosecond. So here the delay is 5. So this is not a very fastest adder. So we are going to design the carry loop adder. What I was talking about the program optimization, I will generally include the pattern. So this one for some and carry, including the optimized design, it will be like you will have four and it's here A bar C E. Okay. So if you consider 1 nanosecond for all the gates as delay, then it will be 2 nanosecond, right? Similarly, carry is also level weighted the same. AB, BCL, UCL. This is also 2. So for unoptimized, it is 2. So if it is a n bit adder, then it is 2n. So this is optimized design. This is optimized in terms of area. Okay. So for this optimized design, it's 3n for a binary adder, for a routing binary adder. Is that clear? So this is a complete design for producing the command CL, and this is the area optimized. We have only 5 bits. For previous design was unoptimized, it has more than 20 bits. So one of the disadvantages is the visibility when I'm transiting from one slide to another, it is not visible. Is that same visible now? Are you able to see the notebook now? Okay. So create is the propagational delay for every binary adder. This is for the optimized design. For unoptimized design, it is 2n. Is it visible for everyone or So can I continue? Is this clear? So one of the bottleneck of the duty carry adder is the high propagation delay. So we want to reduce the delays of the adder. That's why we are going to define the carry overhead adder. In open carry error, it is because of the regular effect. That is, the carry is propagating time LSB. So if we can compute the carry independently without waiting for the carry from the previous step, then we can reduce the delay for the this step. So then it will not be trivial. It will not depend on the size of the adder. So if you can look ahead and compute the carry without waiting for the previous block carry, then in that way we can reduce the delay. So this is the design, optimistic design of the ladder. You have two corners and one gate. So if A and B, if A and B, if then this inputs are 1, this carry is going to be 1. So we don't have to look into this CN, right? If both A and B are 1, then this carry will be 1. We don't have to take into account into CN. So carry will be always 1 when both the inputs are 1. And so this is one carry variable. And this one is any of the input is 1. This is going to be 1. And this P in, when this becomes 1, this will be, this is going to pass this ceiling, right? So this is going to propagate this ceiling. So this is, we can call it just carry propagating. And this is carry generator. So this is an XOR gate. So if any of the input is 1, sorry, 1 0 or 0 1, it will be 1, right? So this is going to propagate the same here. So suppose if we can represent the expression using this PI and PI, this is the output of the half hour. G is the carry, and P is the sum for the first half cycle. So if you can represent the final sum and carry out expression of in terms of P, this half order outputs, it will not depend on the previous block carry. So we can compute the carry for each block independently. For example, for a 4-bit adder, you will have P0, P1, P2, P3. Similarly, you have J0, G1, G2, G3. So P0, G0, P1, G1, P2, V2, P3, V3, we can compute it independently. There is no carry dependency. This is our output of first half order sum, and this is the first half order carry. So Pi is An, X Dn, and Ga is An, Vn. This is a half order output. So here, then sum will be Pi X. Okay, we can only just figure here. So this is the sum and carries for full adder. So if it is a 4-bit carry represented adder, the C0 is the input carry. C1 will be J0, P0, C0. And C2 is J1 plus P1, C1. Here P1, we can write it like J0 plus P0, C0. So from this equation, C1 only depends on the input carry. C2 depends only on the input carry. It doesn't depend on C1. C3, it doesn't depend on C2. It only depends on C0. So we can compute the carry independently. Can you hear me? So this is how we are going to compute the carry independently. If we draw the logic diagram, we are going to draw it. So it will be a two-level logic design. We will have AND gates and OR gates. You can draw it by yourself, okay? For C0, C1, C2, C3, you will have AND gate, then you will have OR gate and the second stage. So carry represent generator. So here you will have the two-level logic design. So when you draw the diagram for this thing, you will have a two-level logic design, and here you will have the half-order outputs. That is, we are going to take it to the label carry independently. So you will have if it is a 4-bit carry represent direct, then you will have bit 3. This is one half order, then another half order. This will be P3, G3, A2, B2, P2, G2. Similarly, in P0, G0, and you will have an input 10. Once you generate the carry in the output side, you will also have one XOR gate for each bit. Time this C3, it should come from like this. So S3, S2, S1, S2, and you will have a carrier. So this is the carry equivalent generator. Now we are going to calculate the propagation delay of the carrier equivalent ladder. So here it is 1. Here it's a 211. Here it is 1. So total it's a constant of 7. Per nanosecond. If you consider a nanosecond as the delay, then it will be per nanosecond. Is this clear? Here it's 1 nanosecond. Here it's a 2 level logic design, so it will be 2 nanosecond. Then here you have a XOR gate, so that will be 1 nanosecond. So constant time is the population unit for the carrying operator for the bit. Am I audible to everyone? Or okay. Now we are going to see the bottleneck of carry operator adder. So previously, for ripple carry adder, if it is for example, it would take 32 bits adder, ripple carry adder. How many full adders are required to implement a 32-bit ripple carry adder? I have found a 4-bit ripple carry adder. For 32 bits, how many full adders are required to implement a 32-bit adder? For 4-bit, 4 full adders were required to implement for the adder. Each bit and then you will carry. So one full adder to perform the additions, 1 bit along with the carry. So for 4 bits, 4 full adders were required. So full adder for 32-bit triple carry adder, you need 32 full adders. Okay. So each full adder, how many gates? 5, right? 32 into 5. So total 160 gates are required to implement a 32-bit triple carry adder. But when it comes to the delay, it was 3x, right? So 32 into 3, 96 nanosecond. So in the optimized design, all the gates are at 2 input gates. But when it comes to a carry implement adder, okay, I didn't draw the logic diagram. You guys draw the logic diagram and understand, okay? You will have 2 input AND gates, you will have 3 input AND gates. Suppose you have a 64-bit carry input adder, you will have a 63 input AND gate, okay? So for the big carry adder, it was only 2 input gates. So we need to calculate in the same way for carry input adder. So for example, if I have a 4 input AND gate, if I want to implement this 4 input AND gate using a 2 input AND gate, how many gates are required? One way we can implement it like this. Okay. Another way, we can implement like this. So for n input AND gate, we need n minus 1, 2 input AND gate. So we are going to calculate the number of gates required for a carry required adder. If it is a 32-bit carry required adder, you will have 32 half adders here. Okay, so this is a 4-bit. So 4 half adders. If it is 32-bit, then you will have 32-bit half adders. So 32 half adder, you have 2 gates, right? One half adder, you have 2 gates. So how many gates at the first here? It will be 32 into 2. And in the output side, you have one XOR gate for 1 bit, right? So if it is a 32 bit, you will have 32 XOR gates. Okay. Now, in the carry generator for the if you will have 2 input gates. Okay, what is the difference between ripple carry adder and carry ripple carry? So ripple carry, we were propagating this input carry towards the MSB of the single bit, then only we can calculate the S3. So we were not able to calculate the C1, C2, C3 separately because for calculating the C1, we need the carry from the previous row. For calculating the C2, we need the carry from the previous row. So the propagation delay for the ripple carry adder was very high, but it was area optimized. So we need to reduce the propagation delay. We will like if you have a 64-bit adder, your propagation delay is going to 192 nanoseconds. So you need to choose the clock period which should be greater than 192 nanoseconds. For example, you have to choose 200 nanoseconds clock period. That is not an unoptimized or efficient way of design. So we are doing for the carry required adder. Carry required adder. In that, we are going to compute this carry independently. That is, we are calculating this carry independently. So if we have the output for the first half adder, then we can calculate the carry independently. We don't have to propagate this carry. We can calculate the C0, C1, C2. C0 is the input carry, C1, C2, C3 independently. We don't have to wait for the previous block carry. So the one of the advantages we can reduce the delay, but the disadvantage is the area is not optimized. It has a very large area. So this will be 32 into 2 plus 32 and carry with generator. So for if it is a 32 bit, you will have 2 input and it's for everything except the input carry. So 31 into 1. Then you will have, like when you draw this logic diagram, you can see how many inputs for each gate. You will understand this thing. And now going the logic diagram, you can refer it later. So 3 input, you will have 33 input AND gates, 33 input AND gates. So we need to represent it as a 2 input gate. So it will be how many gates? 2 input gates. So it will be 30 into 2. Then it will go like that, 29 into 4 till 1 into 39. So when you calculate all the, when you add all the states, you will get around 6,500 gates. So in the big carry adder, it was only 160 gates, but this will come around 6,500 gates. In ripple carry, for a 32 bit, it is 96 nanosecond. But here the propagation delay is a constant. So, but when if you look into carry required also, that is also not a good design. So what we can do is that we can create a critical adder using both carry required and literal carry adder. So what you can do, you can group this carry required. That is like um, you can have a carry requirement adder for 4 bits. Similarly, you can have a 8 such carry required adder of 4 bits. And this 8 carry required adder, you can connect it as a chain like a big carrier. So when you do that, that time the area will be around 224 and the area is 32. So if you compare this is the following like 8 group of 8 4-bit carry required adder in a triple carry adder fashion. So the area is 224. Which is less than 29 times less than carry required. And delay it is 8 times lower because for carry required adder it was 4, right? This is the so 8 times later here. But it is better than the triple carry adder. Triple carry, if you compare, this is it has 1.4 times more area, but it is 3 times faster than the triple carry adder. So always we can have a combination of carry required adder and triple carry adder for an optimized design of adders. There are different types of adders as well. You can explore it. Then coming to the subtraction, suppose if you want to subtract n from a number n, we always take 2's complement of n and add with n. So it will be like n plus 2 raised to n minus n. This is the 2's complement of n. So if n is greater than or equal to n, and the n carry, that is in the case of binary 2 raised to n, will be discarded. If n is less than n, it will be the 2's complement of 1. This will be the 2's complement of the result. So you need to take the 2's complement of the result and place a negative sign in front of it to get the decimal point. Next, I'm going to talk about the overflow. If you have two numbers and any digits, the result is n plus 1. This cannot be accommodated by n plus 1. So I will do this. For example, if this plus represent given and this is going to give 8. So this is the carry one. So for unsigned number, we can find out overflow by using this carry with CI. But for the signed numbers, how we can find out how the overflow happened? Usually two cases. If one number is positive and one number is negative, then result will be a smaller number. So now okay. If two large positive numbers or two large negative numbers, the result in times one. For example, if I give minus by 1 minus 1, this is the two's complement of 5 and it is a negative number, so you have to give sign because 1, then 12, 0, 0, 1, 0, this is the two's complement of 12 and this is the sign bit. So when you add, okay, this one is 1, 0, 1. That was the cavity. Okay. See. So this is the overflow. But an unsigned number. So you need to take the two's complement of, this is the two's complement of minus 70. Here this bit is 1, so sign is negative. So this is minus 70. So we need to take the corresponding limits minus 17. So here, this is a finite, and from this, the carry will be C0, and then this to carry is 1. So this is one power 2. This is one example of power 2. Okay, silent, you will have positive and negative numbers. Outside, you will have real positive numbers. Previously, I was shown this is plus 4 and plus 2. Like, it may not be plus 1, like plus 4 and plus 4. 4 plus 4. Here, you will have positive and negative numbers in the case of unsigned. Another example is plus 5 plus 3. Okay. If we are representing using 4 bit, it's 0, 1, 0, 1. This is a positive number, so you can represent it same way. So it will be 0, 1, 0, 0. So then will not be carry, it will be 0, 0. So this is plus 8. So here there is no overlap. But when the carry from this data to this sign bit is 0, and from sign bit to outside input is 1. That is 0 or 1, 1 or 0, then over 0. Here it is 0, 0, right? Here if it is 0, 0 or 1 or 1, no overflow. This is how we can find out whether overflow happened for the unsigned numbers. You can try out few examples. We don't have time, so I'm quickly moving to the next topic. The main point you need to remember that is that overflow we can detect by observing the carry bit into the sign bit position and the carry out of the sign bit position. As okay, this is from this data to sign bit. This is not carry, right? And this to outside. From the sign to outside. If it is 0, 1 or 1, 0, then overflow. If it is 0, 0, then it's no overflow. 0, 0 or 1, 1, then no overflow. So how we can construct the subtractor using the repeat carry order? We can have a mode so that it can perform the addition as well as subtraction based on the mode. So here, if n is the mode, so n is given as the initial carry. If it is a sign number, that is, if you look, if I am doing XOR with 1, then this A is going to A bar, and this, so this is going to be the complement, right? This 0 is going to become 1 here, this 1 is going to become 0. So when you do an XOR with a number, that is going to give you a complement. So when n equal to 1, this is going to do the subtraction. When n equal to 0, this is going to do the addition. And this XOR gate finally, this is to find out the error code, which I explained in the previous slide. That is 0, 1, 1, 0. In that case, only just find the number error code. So this is for checking the answer, this XOR gate at the final stage. And when n equal to 1, it will do the subtraction, and n equal to 0, it will do the addition. So this is a circuit for the overflow of signed numbers. Then coming to the BCD adder. So BCD, it will represent from 0 to 9, 0 to 9. So if you have two numbers of orbits, which is from 0 to 9, including the carry bit, then maximum we can represent, we can have the adder as 0 to 90. Okay. So A orbit, so you will have A3, A2, A1, A0. Similarly, V3, V2, V1, V0. And carry in, you will have some that is also orbits when carry out. Okay. Here you will have from 000 to 1001, similarly 000. So for this carry can be 0 or 1. Till this, then after 9, from 10 to 15, it will be dawn case. So this is the value inputs till 9. So total you will have 512 combinations, input combinations. Now, how we can construct this BCD adder from the binary adder? So for binary, we can represent, we can have adder results from 0 to 19, right? So if it is a this is the binary adder result. You can have from 0 to 19. So 2, 0, 1, 1, 1, 1. Then 0, 0, 0, 0. So BCD somehow it will be same, right? So into 9 you will have after 9 it will be 1 story. So you need 8 bits to understand. 1 0 0 0. This will be 1 story. BCD you need 8 bits. This 4 bits, 2 bits. So for BCD, how we can do that? If it is 1 0, then this 4 bit we are taking it is 0, then 1. If it is 11, then 1. Here it is 1. Then 12, 1. Similarly, till 90. Sorry, till 19. So here 10 is 16, right? For 10, this is you need to add a 6. So when the binary sum is greater than 9, then addition of binary 6. If you take 16, if you take 10, then it is 16. That is, with 10, you have added 6. If it is 17, then with 11, you have added 6. So there is a requirement of addition of binary 6 to the binary sum, which will convert the BCD representation. And draw the final diagram. This carry will be 1. So from this For binary number 10 to 19, you will have a carry and you need to add 6 for that. Here, you have to add 601 instead. This is also a complete binary array. So in this way, we can construct the BCD array and the binary array. And moving to the multiplier. Suppose you have a 2-bit number. 390. We have for a J multiplier bit and K multipliers with when how many delegates J into K. It's a 2 into delegate. So here it is a 2-bit. So copy per delegates. So into 2. And others that will be J minus 1 into K address. Here 1, 1, copy 2. 2 adders for this 2-bit. And how many parts it will carry? J plus 3 parts. So total 4 parts. Okay, with this we are coming to the end of the recap session. We will quickly go to the problem solving. How many full adders and half adders are equal to add two 32-bit numbers if there is no carry? You can put your answers in the chat box. How many full adders and half adders are equal to add two 32-bit numbers if there is no carry in? 32 full adder, 1 half adder, 30 full adder, 2 half adder, 31 full adder, 1 half adder, 31 full adder, 0 half adder. It is not option A, it is option C. 31 full adder and 1 half adder. It is because there is no carry in. So for the first adder, we can use a half adder. And for the rest of the 31 bits, we can use a full adder. So 31 full adder and 1 half adder. Since there is no carry in, first adder should be a half adder. Consider a carry lookalike adder for adding two n-bit integers built using gates of panning at most 2. The time to perform addition using this adder is this is the time complexity. In this question, the time complexity it is determined by the depth of the carry required logic, which gives logarithmically with the number of bits in the input. So it can be the right answer. Time complexity of log n. Next question, an incomplete repeat carry adder is constructed using 8 full adders. The carry propagation delay of each full adder is 12 nanosecond. The sum delay for each full adder is 15 nanosecond. The worst case delay of this repeat carry adder is so here the carry propagation delay for each full adder is 12 nanosecond. So the time taken to propagate the carry from the first full adder to the last full adder will be 12 into 7. Okay. Plus and the sum delay for each full adder is 15 nanosecond. So for the final full adder, the carry, the propagation delay to get the carry will be 12 into 7 plus 15. So it will be 99 nanosecond. Okay. So option B, option A, 99 nanosecond. Then how many two input NAND gates are going to implement the full adder? Seven. How many about 7? How many NAND gates are required to implement one XOR gate? So provided you have two XOR gates, right? So there are 4 NAND gates are required to implement one XOR gate. So 2 XOR gate, 4 plus 4, 8, and you have also carry, right? So intermediate values, if you take intermediate values, for the AND operation, you will get the carry. So total it will be 9. I will show you the circuit diagram. This is one XOR gate. So the output will be XOR gate. Then it will be XOR with the carry gate. So this will be from when you solve this, you will get finally answer the Excel student. For carry, this will be 0. So total 9 values. You solve the equation in this state. Then you will get the final expression. So total 9 days. The next question, the 8-bit two's complement representation of an integer is, this is the number. What is its decimal representation? So the given representation is 2's complement. So from the NP, we can identify that it is a negative number. So this is the 2's complement. So first you will have to invert it. Then you need to add with 1. So it will be minus 10. Now option A is the right answer. Next question, consider the following statement on power flow happens in two complement addition. Statement 1, both operands are negative and the sum is negative is called error term. Statement 2, both operands are positive and the sum is negative called error term. Statement 3, both operands are negative and the sum is positive is not error term. First statement, one is false. That is, both operands are negative and the sum is negative, then it is called obviously. That is false. And statement two, both operands are positive and the sum is negative, then it is called output. That statement is true. And both operands are negative and the sum is positive, it is not also. That is false. This is both operands are negative and the sum is positive, that is overall. So option B is the right answer. The next question, the number of full adders and half adders required to add two decimal digits in a BCD adder is consider that there is no input carry. Which is the right answer? How many full adders and half adders are required to implement the BCD code? For constructing the BCD counter from binary counter, like the resultant result of the binary counter will be added with 6. So for implementing the binary counter, like for two numbers A and B, if there is no carry in, then we will need 3 full adders and 1 half adder. And after that, we have to do the addition with 6. So there is also for the it will be 0 1 1 0, right? For the first bit, there is no carry in. So you can it is 0 1 1 0. There is no addition for the first bit. Next bit, there is no carry in, right? 1 0. So you need 1 half adder. For the next one, you need 1 full adder. And the next one, you need 1 half adder. The total 4 full adders and 3 half adders. The next question, how many AND gates and adders are required in a 4-bit multiplier? And 16. So if you have n plus n, then the AND gates is n into n. So 4 into 16. 16 AND gates. Then the adders, that is n minus 1 into n. That is 3 into 4, 12. So option C is the right answer. 16 AND gates and 12 adders. So with this, we are coming to the end of the session. Do you have any other particular question? Okay, there is one more question. That is calculate the overall completion delay of a perfect carry overhead adder despite using and and not gates as shown in lectures. Delay of each gate is one time point and it is already there. It's we have already discussed this. Okay. We don't have any particular question and we can take it to the next class. If you don't have any question, then we can wind up the class. Okay. Please compliment. So the given representation is two complement. So you need to find out the decimal representation. For that, first what you have to do, from this, from the MSC bit, we can identify that it is a negative number, right? So we have to find out the decimal representation. So what we have to do, first you need to invert the bits. I would put it in the chat box the answer how you have to do the invert. Just take the complement of it. Then you need to add 1. You will get 10. So answer will be minus 10. Is that clear? Subtraction. Okay. And if you have any other question, you can ask me in the next class. Thank you.